In section 8.4, we're going to take a look at something that we have done earlier in section 8.2, and that is to construct a confidence interval for one population mean. In this section, sigma, which is the population standard deviation, is presumed to be unknown. Now remember in section 8.2 that the standard deviation sigma was known. Now, as we are about to see how things unfold here, just want to remind here that in section 8.2, we're looking at sampling distribution of X bar, and we know by central limit theorem right in here that the sampling distribution of X bar, the probability distribution of X bar, if you will, follows a normal distribution with the center mu of X bar, which is the same as the mean of the population of individual scores that we're trying to approximate or estimate, and this would be the standard deviation of it. So in here, if we standardize this X bar, and this is how we standardize it, the new variable, which is a z-score, z is a variable, this variable is going to follow a normal distribution with a mean 0 and deviation 1. Now what if sigma is unknown? Well, that same variable z now becomes variable t, let's say. The difference, of course, being that sigma is not known, so we replace it with the sample standard deviation s. And this variable now follows, in fact, a different probability distribution. This probability distribution is called a t-distribution. Okay, so now it's often known as a student's t-distribution, and what I have here is I have an excerpt about the gentleman that actually discovered this distribution, Professor William Seeley Gossett. The early 1900s is, I believe, when the distribution was discovered by him. Now, you can kind of read it as it is in here, why the distribution is called the student's t-distribution is due to the fact that Mr. Gossett's employer, which was Guinness Brewery, at the time would not allow him to publish his work, so he still submitted his scholarly work to the Biometrica journal as a pseudonym student. So that's why the student is called the student's t-distribution, because that's how he was submitting his papers in order to remain anonymous. So just want to give you a little background about it. If you want, you can go to Wikipedia. That's where I got this image from. And you can read more about it, and very interesting biography of this gentleman. Now, this t-distribution actually is going to look like so. This is figure 8.8 in your textbook. And what I've done here is, again, done an excerpt of this drawing. Now, this is what the t-distribution looks like. So the distributions that are in blue and in green are the t-curve or t-distributions. And in here, the author, this is from your book again, your author has compared this with a standard normal curve. Notice how, just like a normal distribution, the distribution is also symmetric and bell-shaped. Okay, now, one of the parameter of the t-distribution, that means what we need in order to be able to draw this curve, the blue and the green curve, is called degrees of freedom. That's what Gossett named it. Degrees of freedom is the parameter of this t-distribution. So without it, we wouldn't be able to draw the t-curve. Now, depending on the degrees of freedom, then the t-curve is going to look different. So we don't have a single t-curve. There is a whole family of t-distributions depending on the degrees of freedom. Now, I will flash the formula here for you. And of course, you're not responsible for the formula, but for those who've had maybe calculus or more advanced courses, then they may appreciate what this formula looks like. What I have here is actually the functional form of this elaborate curve, or rather elaborate function. So it's rather sophisticated. complicated function that you can view as I have it here. So again, keep in mind, please, that you're not required to know the form of the function. Again, this is for those students who are interested in knowing what the function looks like. Now, the degrees of freedom, and this is again from Wikipedia. The degrees of freedom in Wikipedia that they use here is this Greek character, this Greek letter, which is called or read as new, as in like N-E-W, new car, new something. So that's what it is. This is how it sounds, like new. We already know about mu. Now here, this is new. Okay, so this is the parameter of the t distribution. And again, you can see here the t distributions that are with 1 degree of freedom is the one in orange. 2 degrees of freedom is the one, I believe, is in purple. 5 degrees of freedom, you get the blue curve. And then it jumps to infinite degrees of freedom. For when degrees of freedom is infinite, the t curve actually turns into a standard normal distribution, mean 0 deviation 1. So the distribution will morph itself into a standard normal distribution. And that's kind of interesting. Now, I also want to point out that this distribution is what we call a central t distribution. The book doesn't call that, but that's what it is. And what we mean by central t is that the center of this distribution will always be 0. There is a non-central version of this where the center of distribution could be somewhere else. Again, you can read these online in Wikipedia if you like to. Now, let me go back up here, and some of the basic properties of this t curve are listed in your book, as you can see. Property number 1, because this is a probability distribution, therefore the total area under the curve has to be 1. And it is 1. It can be shown, but we're not going to show that. The second property of this t curve is that, again, just like a normal distribution, it will extend indefinitely in both directions. That means it will go to plus minus infinity on both directions, but the curve will never touch. The curve will never touch nor cross the horizontal axis. Okay. And the third property tells us that this t curve, as I mentioned, it is symmetric, just like a normal distribution is, and is symmetric about 0. And finally, something that I mentioned earlier is that as the number of degrees of freedom approach infinity becomes very large, then the t curve approaches a standard normal curve. That's a normal 0, 1. Okay, and you can kind of see this here in this figure 8.8 that's in your book, and also the figure that's directly below it. Now, because this is a probability distribution, again, just like a normal distribution, the question is, how do we find probabilities under the distribution? Well, in order to find the probabilities on the t curve, we either use a StatCrunch or a software, or we use a table that's typically in the back of every statistics textbook, and each author has their own t table. So that's what we will be using to answer probability questions about the t curve. Now, this is again an excerpt, a copy paste, if you will, or cut and paste from a table that is in the appendix. This is table 4 in the appendix. Okay, that's what this table is. And you can kind of see that right in here. You see that table 4, that's a Roman 4. And it is in the appendix on pages 9 and 10. So the one that is in here, this is page 9, and this would be on page 10 of the appendix. Okay, and that's what that is. All right. Now, the way this table is constructed, by the way, is entirely different than the standard normal distribution table. If you remember, for a standard normal table, the margins of the table, we had the z-scores, and on the body of the table, we had the probabilities. Well, for a t-table, it's exactly opposite of that. So now, the margin, the top margin of the table, these are actually probabilities. And let me enlarge them for you. And there you go, you can see it. So the top margin here, this is 10%. Subscript 05 means 5%, 2.5%, 1%, double 05 means 0.5%. The body of the table is actually, these are the t-scores. Like z-scores, we have t-scores. And running down the vertical margin on the left and on the right for easily, or for the ease of readability, actually, I should say, he has these degrees of freedom running down the sides of the table along the column on the margins. So you have 1, 2, 3, 4, 5, and so on, degrees of freedom. And then you can see these different t-scores. And the table, of course, runs in 2 pages. Now, how low he goes on page 9, it starts with degrees of freedom. Again, right up here, 1, 2, 3, 4, and so on. And it goes down to, actually it goes down beyond 27. I just had to cut it to where it will fit on my notebook. But it actually goes further. It goes 28, 29, 30, and so on. I believe it goes all the way to 49. 49 on this page. It goes all the way down to 49 degrees of freedom. And then on the next page, which is on page 10 of, what you call it? Oops, didn't want to do that. On appendix, on page 10 of the appendix, then he actually looks at these other degrees of freedom, the other values for the degrees of freedom. Okay. And you can see degrees of freedom now go from like 50, 51, 52, and so on, all the way down to, I have it at 80, but actually it goes down to, there you go. This is the rest of that table on page AP10, appendix page 10. So he goes all the way down to, let's say, 75 degrees of freedom, one at a time, 50, 51, and so on. And then beyond 75, he jumps to, look at it here. Beyond 75, he increases degrees of freedom by 5. So he goes to 80, 85, 90, 95, and then every 100 degrees of freedom, and then he jumps to 1,000, then goes to 2,000, and eventually you have to stop, right? You can't just go to infinity. So most tables don't even do this. They don't go as high of a degrees of freedom as this author has, which is nice. Now, one thing that I want you to note here, by the way, or a couple of things, is this. Let's say, for instance, for 05, if you recall, the Z of 05 is 1.645, right? In chapter 6, we saw these numbers. So these should look familiar. In fact, that's the one exercise we did in chapter 6, section 1, near the end of that lecture. So these numbers should be familiar to you. Now, if you look at these numbers, like at 1.645, which is a Z-score, and if you compare it to the entries directly above them, see how these are very close to 1.645, right? Right in here is where they begin to become very close to 1.645. And if you look at the degrees of freedom, you go 300, 400, 500, and so on, which again reinforces the generalization we made earlier. As the degrees of freedom increases, a T becomes practically a Z, a standard normal distribution. So there you have it. So we can get our T-scores from this table. Okay, now actually we'll do an exercise here in a moment. And in fact, there you go. And I also show you how to do this, by the way, in StatCrunch, this exercise. We can get these T-scores from StatCrunch. So allow me to do this, first of all, from the table, and then we will actually look at it from StatCrunch. So exercise number 82 reads, for a T-curve with degrees of freedom equals 17, use table 4 to find each T-value. So in part A, we want a T of 0.05 and 17 degrees of freedom, right? So 05 and 17. Therefore, I'm going to go up here with 17 degrees of freedom. And let me show you. Here is, I'm going down the degrees of freedom right up there. 17 would be here. And then the O5 column, that's the column of O5. Now, you're going to go across. There you go. That's 17 degrees of freedom. And down the column of O5, and where the 2 cross, the number that sits there, right? This number that sits here is 1.74. And there you go. That's what our t-score is. So I'm going to write that. 1.74. That's what this score is, 1.74. What I have done is actually, to be accurate, I went to StatCrunch and I drew these curves with 17 degrees of freedom. And I told StatCrunch I want 5%, 2.5% for part B, and in part C I want 005 area to the right. So this is indeed the graph for part A. Okay, and again, I will show you how to do this in StatCrunch in a minute. So the shaded region, the red zone here, what's marked in red right in here, this is going to be 0.05. That is the area to the right. Now, the author, by the way, this is exactly what the author does. I forgot to mention that. So if you look at, for instance, let me erase that. If you look at what the author has given us here, right in here, this is the area to the right. So his pledge, the author's pledge to us, is that he will give us the area on the right side. So the table that you will be using, if you use this table in this book, he will always give you the area to the right side. Okay, so please keep that in mind. Not to the left, not in between. And for what we do from here on out, we really don't need the area between. We're just going to focus on the area above and below. And of course, to get the area below the curve, we can use the symmetry of the distribution. Okay, so there you go. Now let's do part B. In part B of that, let me erase O5 now here. We don't need this one, and we don't need this. So for part B, he wants us to find a T of 0.25 now. So the middle column is 0.25 with same degrees of freedom, 17. So this time I'm actually going to go across until I come to the 0.25 column, and right in here, the two meet at 2.11. So that's going to be our t-score, 2.11. And that's what this number is. Of course, the t-score is here, right? These are the t-scores. There you go. This is a t, this is our t, and so on. T is 2.11. The area to the right is 0.01. Oh, actually, no. Was it 0.02? It was 0.025. So sorry. Yeah, in area is 0.025. No biggie. I just erased it. Okay. Here you go, 0.025. Okay, and finally, so this was part B, the one we just did. And this would be for part C. Okay, and in part C, what we want to do is we want to find the T, so the area to the right is now 0.005. So I already have it here. This is the tail area. You see that tiny region? From there to positive infinity is 0.005, 0.5%. The score that goes with that is, and this time we're going to erase the 0.25 and we're going to go down, which column? We're going to go to 0.05, right? That's the very last column right here. So keep going across, and right in here, that's where 0.005 is. There you go, 2.898. 2.898, and that's the number we want to write, 2.898. That's this score right in here. Okay, and again, the horizontal axis are the t-scores instead of what we used to have, z-scores. Now we have t-scores. Note the distribution looks almost, it is symmetric and just like a normal distribution. Okay, now let me go to StatCrunch and show you how to do this. So remember, we want to do degrees of freedom 17 and then 0.5, 0.25, 0.05. So to do this, I'm going to go to StatCrunch. I already have, I believe, StatCrunch. I have been timed out, so let me actually log back in here, and then once I do, there you go. Let me log in and put my password here. Sorry. Okay, let me put my password here. And this should take me to StatCrunch. Actually, it will take me to my MATLAB, which is good. That's where I want to go and show you exactly how to bring up StatCrunch in case you've forgotten. And actually, let me X this out and go back in here. There you go. I'm in StatCrunch. So this is the page that would come up. I mean, I'm not in StatCrunch. I'm in my MATLAB. So I'm going to go to StatCrunch. And I would like to go there with data sets from the textbook. Let's see if it'll bring it up. And yes, there's a StatCrunch. So now, in order to do our t-scores, so I'm going to go to Stat. And then we go to Calculators. Now remember, here we have a whole list of well-known probability distributions. We're going to go to a t. Now StatCrunch uses capital T. Usually we use lowercase t, but whatever, doesn't make a difference. And here you go. So you get the t, nice looking t distribution. This is the default with 10 degrees of freedom. So I'm going to change that to 17 degrees of freedom. And we want the area to the right, so I'm going to change that to greater than or equal to. And because we want the area to be 0.05, I'm just going to type in 0.05 here. This is actually the area to the right. And what's going to pop in here? Okay, that's going to be the t-scores. And compute, and there you go. So that's how we get the numbers from StatCrunch. StatCrunch shows 1.7396, round to 3 decimals. It's going to be 1.74 actually, right? 1.74. And what do we show here? We have 1.74 from the table. Our next number at 025, the t-score is 211. 211. So let's go back here and change that to 0.025, and we should get 211. There you go, 2.1098, blah, 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 which rounds to 2.11 to the nearest hundreds. And of course, if you want the area to the left, there you go, to the left, I want it to be 0.025, 0.025. By symmetry, it's going to be negative 2.11, correct? And of course, in StatCrunch, it will give you the area between also. So well, we shouldn't need that. We just primarily use area to the left or to the right. So let me go back up to area to the right and do part C. In part C, we want the right tail to hold 005 area. And that t-score is 2.898. Again, rounded to 2 decimal, it's going to be 2.90. And 2.898 is to 3 decimals. And there you go, 2.9898. So this is how you do this in StatCrunch. Again, hopefully you follow that. It's pretty easy to do. Now let me go back in here, and with that now we actually want to now write the formula for our confidence interval. Remember, in case you forgot, that was the title of this section. Remember what we wanted to do? Lost track of that. We want to construct confidence interval for one population mean when sigma is known. So to do that, our formula is going to be, here it is. This is the formula that I have for you. The formula for 1 minus alpha 100% confidence interval for mu. That's what we want to do. Okay, this is what we want to do. And again, it's important, the assumption is that sigma is unknown. If sigma is known, we're in section 8.2, we use a z confidence interval. This will give us a t confidence interval. And I have the formula for you. It's going to be x bar plus or minus a t times S over root n. Again, if you note here, the difference is that in previous section, 8.2, that was sigma, right? We no longer know sigma, so we replace it with the sample standard deviation. That's what S is. This highlighted S, this is the sample standard deviation. Okay. Now, of course, which T curve are we going to look at? Well, we're going to look at the T with the right tail area, alpha over 2. And the degrees of freedom for this confidence interval for the T curve is going to be n minus 1. N being the sample size. And with that, here is what's in the book. So this is called the one mean, 1 mu, T interval procedure. And the three assumptions here are important. The first one is that we have a simple random sample. If the sample is not a simple random sample, the formulas for this part here would be different. The normal population or large sample, this is so we have the correct sampling distribution of X bar, remember. Large sample, keep in mind, remember what large sample was for us? I'm sure you all remember that, right? That was in chapter 7. Also in section 8.2. Large samples for us, that means n must be at least 30, correct? Again, it is large in the eyes of central limit theorem. For us, 30 is actually not a large sample, but it keeps the theory happy. Okay, and there you go. The formula is right down here. I put mine as a plus minus, but the author here actually has split it into two parts, but they're the same things. Okay, and then there is a note down here that this confidence interval will be exact if the population we sample from is normal and it's approximate if the samples come from populations that are not normal. Okay, so and it's fairly a robust confidence interval, even if you have departure from normality. This does a good job at establishing the confidence interval. Now, with that, let's actually take a look at an exercise here. So again, this is an exercise from your book. This involves TV viewing. Okay, this exercise involves TV viewing. Okay, now the question or exercise is, according to communications industry forecast published by Veronis Suler Stevenson of New York, the average person watched 4.55 hours of television per day in year 2005. A random sample of 20 people gave the following number of hours of television watched per day for last year. So there you can actually see these numbers now. Now, just before I actually read this, I just want to do something on the side for you here. This is not again in your book, but it's worth noting. Excuse me. If you look at these numbers, you see how variable the numbers are. On the low side, the low end, you have someone who's watching about an hour of television per day, right? These are watched per day. And then on the high side, you have people that are watching as high as in the 9 hours. This one particular person watches 9.1 hours. So that is a wide range of variability that's between the scores. So what I've done here on the sidebar, there you go. I have actually looked at this thing that's called coefficient of variation. Okay, we haven't talked about this. I may have in class, but in general, you may have forgotten it, or I may not have talked about it. But what this coefficient of variation does is quite interesting for us. And I'm just doing this again on the side for this exercise, because that ratio of 2.297 to 4.76, the ratio of standard deviation to X bar, which is what coefficient of variation measures, CV for short, coefficient of variation measures, for this exercise is about 48.3%. That is a high CV 48.3%. That's what the CV is. And you can see the standard deviation is half the mean, which is quite large. So what does that tell me? That tells me that this data is very highly variable. So if I want to know from this data, if they tell me on average this person watches 4.5 hours of television per day, I'm not sure if that's really going to be an accurate figure. So 2 reasons. One, sample is small, only 17. And second, the CV is so large. Now, what kind of a CV do we like in order for the mean to be a representative, or as we call the typical score, represent a typical score in the data set? The CV should be about 5%. That's what the CV should be. That's actually a percent symbol right here. Okay, sorry, let me clean that up. There you go. That ought to be, that's going to be 5%. Now look at this CV that we have, almost 10 times as much. So standard deviation should have been about 0.2, okay, 10 times less than what it is now, in order for this data to be pseudo-reliable information. So anyway, I just want to mention that in passing. And let's do the exercise now. In part A, find a 90% confidence interval for the amount of television watched per day last year by the average person. Now notice, by the way, he has given us the summary statistics. This is going to be important later on when we go to StatCrunch. Okay, let me write these 3 pieces of information here so you remember it. Sample size was 17. The standard deviation he does is 2.297. And X bar 4.76, so we don't have to do it ourselves. So first of all, doing it by hand, I just went to my formula. In order to use the formula, there you go. In order to use the formula, well, we need a t-score, right? For 90% confidence interval, alpha is going to be 10%, right? The other side of that, that's my uncertainty level. Right in here is the uncertainty level. Half of that is going to be 5%. So the degrees of freedom, which is n minus 1, sample size minus 1, produces a t. So we're going to look in the table in the back of the book for a t with 0.5 area to the right. And, oops, I have 17 and was, oh, sorry, n is 20 here, not 17. What am I thinking of? Okay, so it looks like the sample size was 20, and indeed it is. This is a 4x5 matrix of observations. So the sample size, sorry about that, let me fix that. So the sample size is 20. Okay, and that's how I got the 19. Okay, so that was a good check. See, I didn't use the sample size here, no. Okay. So sample size is still small. I said 17 earlier with the CV, but it's 20, still small. Anyhow, so if I look at the table T05, 19 degrees of freedom, you get this number 1.729. Now let's go back up to the table trying to find this number, 05 and 19. So I'm going to go up here, 05 and 19 degrees of freedom. And let's see, erased it. Oh yes, I said 17 because that 17 I just removed was still on my mind. But this time we have 19 degrees of freedom, and it was 05 on the right side. So there's 05, 19 degrees of freedom. And again, where the 2 meet, right, there and here, these 2 are going to meet at 1.279. And that's how I got the number. That's the t-score, the t-multiplier that we need for our formula. Okay. And with that, now I'm going to go back down. And this is where I got that number from. The 1.279 that came from the table. Okay. And right in here, table in the appendix, page AP10. Okay. Now, the formula is the next thing. So I went ahead and just copied the formula. I had x bar plus or minus t times s over root n. X bar was known. T-score we just found, right? The t-score we just found from the table. This one. And multiply by the standard deviation over let's see, over square root of sample size. Oh, hold on, I didn't do this 4.6. Let me fix this one, sorry. That should be square root of the sample size. The sample size was 20. Okay, so now if I do this on a calculator, the right side of this that I have here, the right side, let me do 2.297 times 1.729 divided by square root of 20, and I got it should be 0.89 actually. So let me fix this one. That's going to be 0.89. And then once the way you handle the plus or minus, once you subtract 0.89 from 4.76 minus 0.89, the low end is 3.87 actually. So let me fix this one. I'm glad I checked it. 3.87. And the upper limit of the confidence interval is going to be 4.76 plus 0.89, and that's going to give me 5.65. Okay, 5.65, and that's what this is. Now, the thing that's to the right of plus or minus, right in here, this is our good old familiar margin of error. Remember, we talked about that in previous section 8.3. So here's the interpretation now that's coming up in a moment. I'll interpret it in a moment to do part B, but something I want to do real quick, by the way, in this one, he didn't ask for it, but remember the assumption number 2. Let me go back up here for this procedure. The second assumption here, this one, is normal population or large sample, where the sample for this exercise is 20, so it is not large. So we need to check the normality here, and that's what I did. We're going to use a QQ plot for normality, and I did, and I'll show you how that's done also in a moment. But there you go. Based on the QQ plot, it looks like it's reasonable to assume the viewing times are normally distributed. So we have the go-ahead from the assumptions to do this formula. And of course, I'll show you that in a moment in StatCrunch. And I ran this in StatCrunch, and I actually found these numbers. Let me see. Remember this one I just adjusted up there. 3.87 is what we got, and 5.65. 5.65, that's what this was, which is now, there you go. I was wondering how come these numbers were off somewhat. Okay, so not bad. Again, off a little bit because in StatCrunch they actually use a t-score to like 16 decimals, something like that. Okay. And so you can see the scores are pretty close. We both got the same confidence interval. Now remember, in again StatCrunch, this is U stands for upper, so this is your upper limit, and the L here stands for lower limit. Okay, so that's what that is. You have the upper and lower limit. DF here stands for degrees of freedom, sample size minus 1. The sample mean is 4.76. Now this number, by the way, the standard error, this will give you the standard error is the standard deviation of the sampling distribution of X bar. In other words, if you remember, we have sigma over root n. Now we don't have sigma, we have S because sigma is unknown. So if you do S over root n, the standard deviation, remember, was 2.297, right? Over the square root of sample size is 20. If you do, I promise you're going to get 0.514. I'm just rounding that to the nearest thousand. Okay, and that's what that is. Which means if I draw this distribution here, this is approximate distribution, sampling distribution of X bar. The standard deviation is that. Okay, and the center of it, of course, is the average, which is 4.76. Okay, and that's what that is. Okay, so just want to point out what is this standard error, because it's going to keep popping up in our StatCrunch outputs in this chapter and in almost every chapter from now on. Any chapter we do confidence interval, and in chapter 9, our next lecture will be in chapter 9 for hypothesis tests. You're going to get similar information. Okay, and I guess I'm good with this information. And let me see. Wow, there we go. That's pretty much, we're done. Oh, the interpretation, and then I go to StatCrunch, show you how to do this whole thing in StatCrunch. Now, in part B, the interpretation, we are 90% confident the amount of TV watched per day in 2005 by the average person, okay, by the average person, is somewhere between almost 4 hours to 5.59, almost 6 hours, right? 4 hours approximately to 6 hours. That's how long they spend watching TV per day. And again, I'm sure most of you don't do that. So remember, this is a highly variable data. So this isn't really reliable. I don't think it's that reliable because the variability is so high. So is the CV, the coefficient of variation. Okay, having said that, now let me go to StatCrunch and actually do this whole thing in StatCrunch, exercise number 94. And with that, exercise number 94, and here we are. So I'm going to chapter 8, exercises, scroll down to number 94, right in here, click, and it brings up the exercise. Here's the raw data. Now we're going to run this two ways. Okay, we're going to run it using the information that he gave us. First of all, remember he gave us X bar and S, and I said I'm going to keep track of that for StatCrunch, so we're going to do that. You go to StatCrunch. In section 8.2, we went to Z stats, right? In section 8.4, we go to T stats. And we only have one sample here, right? One sample. Now, I'm going to input summary information. Now, let's see what happens. See, with summary information, StatCrunch is ignoring all of the data that is in this column. It's going strictly off of what you provided. So I'm going to provide the sample mean, which was let me see, that was 4.76, right? So we're just going to go ahead and put these numbers in. 4.76. The sample standard deviation, the author gave us 2.297. And of course the sample size was 20. See, so this is what we mean by summary statistics. See, we gave it a summary, and we want to do a confidence interval. So you click that radio button, you check that, and our confidence level here was 90%, and there we go, 0.90 or just 0.9, doesn't matter. And that's pretty much all we want here. And I'm going to hit compute, and look how simple that is. So this is the numbers that you actually get for this one. I'm not sure. What did I do? Oh, I'm sorry. Let me go edit. I know what I did. See that number 2.297 is, I didn't put the decimal, I put comma, so that's 2,297. Let me backspace and put the dot. Now that looks good. It's no longer 2,000 and change. Compute, much better. And there you go. These are the numbers that we were expecting, right? These two, this one and this one, right? So those are the same numbers we got. So that's one way to run it. Let me X this out. And here's the other way you can run this. If you're not given summary statistics, that means you're not given the deviation and you're not given the sample mean. So you go to T-stat, one sample, and this time I'm going to go with data. And this time now StatCrunch says, okay, well, where is your data? So it's in the column time, right? Left click once. It's in this column, time column. And what else do we need? See that hypothesis? That's chapter 9. We're just going to do confidence interval, change that to 90%. Notice I'm not going to give it the standard deviation, and I'm not going to give it the mean. I don't need to, because StatCrunch now sees the data and it will internalize those information and it will compute those or calculate it itself. Okay, and that's all we want here. Hit compute, and of course there you go. You see that? You get the exact same information. Let me bring back our session results. It was this one, and I'm just gonna put these kind of side by side so you can see that these are the same information, right? Now notice, by the way, they are off a little bit. This information and this one, that's 3.8717. This is 3.8719. The reason this is off, the one on the left is off, is because we gave it the summary statistics. The author rounded those numbers when he provided it to us. So the more accurate numbers are the ones on the right side, okay? Because StatCrunch actually carried more decimals in computing the mean and deviation. And let me show you what I mean one last part, and then we'll move on away from this. Summary stats by columns, time, and I just want to show you here the mean and standard deviation to see this is what I'm talking about. Let's see, the mean is 4.76, so that number is exact. So StatCrunch and your author are using the same numbers. But this other number we used was 2.297, right? Summary stats 2.297. But notice now StatCrunch, when you tell it use the data and you don't give it the summary statistics, that's what it's using. And that's causing the disparity between the two outputs. Okay, now if you do this in, let's say, MyMathLab for the exams, then just do what the problem suggests. If they give you summary statistics, use summary statistics. If they don't, then use the data. And let me go back to this. I think that's about it. We covered a lot of grounds, and good grounds at that. And of course, we're done, I believe. So yeah, we're done with this section. Thank you for your attention, and I hope you learned a lot.